Hello everyone, this is Mr. K, and today we're going to go over graphing the derivative based on the graph of the original function. So first we're going to use this as my original function. And so something to keep in mind is that the derivative is always, it's like a representation of the slope of your function. So here, my first example, I have a slope that changes, but for the most part, it's remaining constant. So like when I look at this first piece here, I have my coordinates for this point as -4, 0, and the coordinate at this point as 0, 4. If you use the slope equation to calculate the slope between these two, the slope would be 1 over 1, or a slope of just 1. So that's the value of my derivative function for this entire interval from -4 to 0. So when I go to graph my derivative equation, I'm going to have my derivative is going to equal 1 on that interval. And now we use open dots just because, like, whenever we have corners and things like that, technically the function is not differentiable at those points. So that's why we're going to use open dots for our derivative function here. And now you can follow the same procedure for the other intervals. So like here on the interval from 0 to 1, I can calculate the slope using these coordinates, and the slope would be -4. So now for my derivative function, I'm going to have that equal to -4 on that interval. Here, the slope is 2, again using coordinates. So I'll have my derivative function equal to 2 on that interval. And then for this last part, you can calculate the slope, but the slope is just 0. There is no slope because it's a flat line. So because of that, I know that my derivative function is going to equal 0 along that interval from 2 to 5. But we don't always have nice straight lines like that. What if we had something that has a little more curve to it? So if I have a separate example here, let's say my function looks something like this. How could we get at least a sketch of the derivative function? So the first thing that I do is I locate anywhere where I know my derivative or my slope is 0. So that's going to occur at all of these minimums and maximums. My derivative is going to be 0 because that's where, like, it's technically the slope at those points is going to be 0. So I know for my derivative function, it's going to equal 0 at those spots. So I mark those on my graph first. Afterwards, now I need to figure out, okay, is my derivative positive or negative? And really, the derivative is going to tell you whether something's increasing or decreasing because a derivative represents your slope. So when I look at the graph here, I see that it's decreasing as I go from left to right, which I know means that my derivative function is going to be below the y-axis because it's going to be below the x-axis because it's going to be negative. So I know that I'm going to start down here and it's negative, but it should be approaching that 0 value some way, somehow. Okay, so now my derivative's negative because this is decreasing, but then once I hit that minimum, now my function starts to increase, so my derivative becomes positive. And then typically mathematically speaking, your derivative is going to have a maximum or a minimum right in between these two. So that's called a point of inflection. That'll be a different video. But just know that this, I know, is going to level off because it's got to come back to this to meet this second 0 here, because I see that my slope was 0 here because now I have a maximum. So this is going to come back down, and I see now my original function is decreasing, so my derivative needs to be below that x-axis again. It needs to be negative. So it's going to come down, but then shortly thereafter it's going to turn right back around because it's going to have to get to this 0 value as well, because I see that this is going to start increasing again. So then we return back up there, and that is an example of how you can take your original function and make a graph of your derivative. And note that they kind of follow each other. And then the other thing that I would note is that at minimum, the original function is going to have an exponent of 4, because you see we'll have 1, 2, 3, 4 different points where it's increasing or decreasing. And you notice that the derivative is going to have a minimum exponent of 1, 2, 3. So at minimum, this is going to be x to the 4th. The derivative will be x to the 3rd. It's also kind of a clue as to the power rule for derivatives when we start taking derivatives using the shortcut method, which will be again in a different video. Hope you found this helpful. Thank you so much. Have a great day.